So here we've got a specific example where the stereochemical consequences of the E2 reaction can be seen. So imagine we had this starter material. We are going to see it gives rise to one specific isomer of the alkene, and if it gives rise to one specific isomer, it is going to be stereospecific. What we're seeing is if we have a different isomer, stereoisomer of starter material, we're going to get a different stereoisomer of the alkene. So these two, we're exemplifying this example with our diastereoisomers. So remember, these are isomers which are not related as object and mirror image. So what we've seen, this centre here is going to be the same, whereas this centre, let's put a triangle, is different. So that's why the diastereoisomers, one centre is the same, the other stereochemistry is different. This one here is up methyl, this one here is down methyl. So what we can do in our E2 reaction is we can redraw these to place the hydrogen and the leaving group anti-periplanar, because in your notes and on a previous example I showed it's better if the hydrogen and the leaving group are anti-periplanar. It's going to be better for the E2 reaction in terms of the sterics and the energetics. So effectively what we're doing then is we're having to use our base to pull off our hydrogen, to kick electrons in, to kick out the bromine. So when we redrew this to have the hydrogen and the bromine anti-periplanar, this is the orientation that the groups will be in when we do our elimination. And what we can see is our phenyl here, so let's use a red colour. Our phenyl is sticking out and the hydrogen is sticking out. So that means that here, this hydrogen is this one here, the phenyl and the hydrogen are on the same side. What we're also seeing in this orientation is the methyl and the phenyl are on the same side. They're both sticking away from us. So we've got our methyl and our phenyl on the same side. We've got our phenyl and our hydrogen on the same side. So from this one orientation here, what we find, this was defined by the nature of the stereochemistry in the starter material. So this is just redrawn to put our hydrogen and our bromine opposite to each other. The orientation then of the alkene is going to be influenced by where the groups are in this when the transition state forms in the E2 reaction. And because the phenyl and the hydrogen are on the same side, they end up on the same side of the alkene. The methyl and the phenyl are on the same side, they end up on the same side, and we get that one stereochemistry of the alkene. Because it's stereospecific, we're saying that the stereochemistry of the product will depend on the stereochemistry of the starter material. So let's just exemplify that using this different diastereoisomer, where, as I say, we kept the stereochemistry the same here, where we got the dot, but here we've got it different. So if we redrew that to put our hydrogen and the bromine opposite to each other, and if we used our base, so doing the same thing, E2, loss of the hydrogen and the bromine in the same step. So what's the orientation of the groups going to be in the product? Well, we've got the same thing. We have got a methyl sticking up and a hydrogen sticking up. So that means here, this is that hydrogen, we've got the methyl and the hydrogen are both pointing towards us, so they're both going to be on the same side here. We've got the same thing to consider here. We've got the phenyl on that carbon and the phenyl on that carbon. They're both pointing away, so they're both on the same side. So that puts both of them on the same side. And so when we look, this is now a different isomer to this, and that is because we had a different isomer here compared to this one. So this is complicated example, probably one of the most complex things you'll look at in my course, but what we've hopefully shown is that the reaction is stereospecific. So if you have one isomer of starter material, when you go through the transition state with the hydrogen and the leaving group anti-periplanar, you get one isomer of product. If you'd have a different isomer of starter material, again when you go through the transition state with the hydrogen and the leaving group anti-periplanar, you get a different isomer of product. Again, why is this important? Well, because in drug design and synthesis, when we are looking at making molecules and we want a specific isomer because it will have a specific biological or therapeutic property, it's useful if we can control the mechanism and we understand whether we're going to get single or mixtures of isomers. That can help us when we're making the right compound.